In this video, we explore the intermediate value theorem, really the first theorem that uses the idea, the definition of continuity to kind of talk about how a function will attain the intermediate values over some interval. I want to go through the kind of motivation for this theorem. Say you have some function here. Let's actually use some function f of x is 9 minus 1/4 x squared, and I've got two x values here, 1 and 5. I want to point out that this function is a quadratic, and therefore we know that it's continuous on the real line, right, from minus infinity to infinity. Okay? And I've tried to sketch it in there a little bit. And what I want to look at here is these two x values and their corresponding function values. So if I take 1 and I plug that into my function, I'm going to get 35 fourths. And if I plug 5 into my function, I'm going to get 11 fourths. Okay? So those are the corresponding y values. And what this intermediate value theorem is basically going to say is that when I have a continuous function like this, I'm going to basically hit every value in between those two y values. And there's going to be an x value between my 1 and 5 there that will correspond to that y value. Let me write some things down here for us. Since f is continuous, and that's really a crucial part of this, on the interval from 1 to 5, f will achieve every value between 11 fourths and 35 fourths. Okay? Every single number between those on the y-axis here, my function will achieve all of those values. And there's going to be a c, an x value between 1 and 5, such that f of c is that value that my function attains. Okay, so take for example when y is 8. Okay, my function is going to attain that value because it's continuous, and between 1 and 5 there's a corresponding c, I call it c1 here because I'm going to do another one, that is going to give me 8 when I plug that c into my function. Say -5 for a y value. There's a corresponding c that when I plug that into my function, I get 5. Okay? So let me write out the theorem for you in all its details, and I want to kind of go through the logic of how it works, and then we'll look at an example. So here's my intermediate value theorem. If f is continuous on a to b, and f of a is not equal to f of b. So when I plug in those endpoints into my function, I need to get different values. Okay, if that doesn't happen, then this theorem can't be applied. And k is any number between f of a and f of b. Okay, we write that mathematically using some notation here. We say k is in the interval from f of a to f of b. Right, so we're saying that k is between those two values here. Then there exists a c between a and b, so I want you to pay attention here. This c is going to be an x value because a and b are also x values, right? Whereas k is a y value, it goes between two y values, such that f of c is k. So let me draw a picture here. I've got a function, and I've got two y values. So hopefully this picture can help shed some light on what this theorem says and kind of what it goes through, and hopefully making some connections with the previous slide. So I've got a function, looks to be continuous, right? Two x values, a and b, and two corresponding y values. And of course those y values are definitely not the same. We've got that pretty clear, right? F of a and f of b are definitely different. For any k, so any y value that's between f of a and f of b, since my function is continuous, there's going to exist a c in between a and b such that f of c is k. Okay? That's going to work for some other k. Right? For any value I choose between f of a and f of b, there's a c such that when I plug that c into my function, I get that value. So f attains all intermediate values between f of a and f of b. Okay, any k. There's a chance, however, that this is broken. Okay, say I change my function a little bit, and right away we see that this is broken because my function is no longer continuous, right? So if you look right here, my function is not continuous anymore. But what happens in that situation is I can find a k. Now, there is some k or some c such that f of c is not k. Right, so there's no corresponding c value. There's no corresponding c down here that when I plug it into my function, I get that k value. This is not equal to. Okay, so this part that the function is continuous is definitely required in order for this theorem to be correctly applied. Okay, I have to have a continuous function for it to attain every value between two y values. Okay, let's look at an example. Where this theorem is used most is to locate roots or x-intercepts. Okay, so the example I want to go through, let's use the intermediate value theorem to show that this function, f of x is x cubed plus 2x minus 1, has a root on the interval from 0 to 1. Okay, so I'm going to try to do this without drawing the function because that's kind of going to give it away, but maybe I don't have a good graphing utility on hand, or I have trouble figuring out exactly what that x cubed, that cubic function looks like. I know some things, but I'm not exactly perfectly clear. I want to verify that there's a root between 0 and 1. Okay, so I have to make a couple observations. First, I know that my function has to be continuous, and it is because it's a polynomial, right? It's a cubic function. We know polynomials are continuous. We're good to go there. The second bit is I need to know that f of a and f of b are different, right? And I've got an a and b here. I've got an a and b of my interval. So I'm going to evaluate my function at those two endpoints. I'm going to say f of 0, 0 cubed plus 2 times 0 minus 1. That's going to give me a negative 1. I'm going to do the same thing, plug in 1, and here I get a 2. Okay, so we got to notice some specific things about these two values, but the first bit is that they're different. Okay, f of 0 and f of 1 are not the same. That's good. So I'm still under the criteria to apply my mean value theorem. So since my function is continuous and the endpoints are not the same, that when I plug in the endpoints, I don't get the same value. That means that for any k between f of 0 and f of 1, there's a c such that f of c is that k, okay? But what I want you to notice is that f of 0 is negative and f of 1 is positive. So by the intermediate value theorem, there exists a c in our interval from 0 to 1 such that f of c has to pass between negative 1 and 2. F of c, if it passes between a negative number to a positive number, it's got to cross the x-axis. It's got to be 0 in between a negative 1 and a positive 2, right? Since those endpoints have different signs, right? I know that my function is continuous, and since it's continuous and the endpoints are different signs, then I'm going from a negative to a positive continuously. I have to pass through when y is 0. I have to pass through the x-axis. Okay? Let me try to sketch a graph that will help me kind of verify this. Let's put some points here, 0 and 1. And we know that f of 0 is a -1 and f of 1 is 2. Any smooth continuous function that I put between those 2 points has to cross through the x-axis. It could look like that, maybe like this, or like this. But either way, my function has to cross through the x-axis. There has to be at least one root between 0 and 1. There could be more, but I know for a fact that because my function's continuous, it's got to pass through those 2 points, and that means that it's got to cross the x-axis because one of those points is negative and the other is positive. If I would have plugged in an endpoint, if I would have plugged in 0 and got a positive, and the plugged in the 1 and got another positive, then I couldn't say that I crossed over the x-axis. I wouldn't be able to tell that. I just know that it would go from one point to the other with no breaks or jumps. Okay, so this is where intermediate value theorem really shows its strength, usually looking for roots or solutions. There are a couple other applications for it, but this is kind of the main one that I wanted you to see. Thanks for watching.